Started. First, I want to wish all of you well. I hope you are healthy. I hope you are weathering this craziness and that you have support in your lives. I hope you're looking forward to spring break when we all have just a little bit more breathing room to figure out this transition. I also want to reiterate something that I said in an announcement that the GSIs are actively working with me this week to figure out how to revise our design project so that it works better in these trying circumstances. So we are going to be figuring that out in the
Cancel the
next
project,
few
please.
days, and we'll let all of you know. So without further ado, I'd like to introduce our speaker today. Rob Pena is one of my dearest friends, and I was so grateful when he agreed to give this lecture for us on a topic that he has a great deal of expertise in. So I feel fortunate on many levels. Rob was actually one of my first GSIs for 140 back in, I think, about 1986. I had just started teaching, and Rob was in the MArch program. But our life paths were such that we were actually about the same age. And so after Rob left school and became a faculty member, we became colleagues and fast friends. So I'll be very brief. Rob is currently a professor and graduate program coordinator in the Department of Architecture at University of Washington. He also has a great deal of professional experience in multiple states, including working with the University of Washington Center for Integrated Design, where he collaborates with design teams on the development of high performance and net zero energy buildings. One example being the Bullitt Center in Seattle, which is the largest building to receive the Living Building Challenge certification. So I have been so inspired by Rob over the years. I hope you enjoy his lecture today as much as I know I will. So with that, I'm going to turn things over to Rob with much gratitude. There you go, Rob.
Great. Thank you very much, Gail, for that warm introduction. It's a great pleasure for me to come back to ARC 140. Let me see if I can get this to work. Slides want to advance. There we go. It has been a long time since I last instructed at Cal. I taught a graduate design studio about 20 years ago. And even longer ago, as Gail said, I was a GSI for ARC 140. And I took that knowledge into practice and then eventually into the classroom. So I'm grateful to Gail's mentorship all those years ago. Back when I was a GSI, I was actually a thermal comfort model. Here you can see me and my other GSI colleagues in I think we were ahead of our time fashion-wise, facial hair and fashion. I think we fit right in today. Demonstrating 0.7 to 0.8 Clo. This is not only illustrates 0.1 to 0.4 Clo, it also speaks to Professor Brager's power of persuasion in the interest of education. So be warned, you all. What I want to do today is present some of the key principles and give you some examples of some of the things that we can do as designers to really pull from probably our most influential sensory opportunity, our best tool in our design toolkit to design really meaningful architecture. And as I do this, I'd like to pose a question to you that I'm going to ask for some responses from a little later. And that is, first of all, why does it matter? Why does daylight design matter? But also, what are our opportunities as lighting designers to use this powerful tool? And I want to start by returning to some of the core principles that you saw on Monday and in your readings. And the first thing I think we need to remind ourselves of is that daylighting, light from the sky, is incredibly dynamic. And that's a wonderful thing. But generally, we think about the two ends of the spectrum, clear skies, and this idea that when you have the brightness of the sky, now I'm not talking about the sunbeam, but the brightness of the dome, that the darkest part of the dome, which is about 90 degrees from where the sun is about a tenth as bright as that sort of white washed out area around the sun itself. And then at the other end of the spectrum, and we experience a lot of this in Seattle where I live, is this idea that on a uniformly overcast day, the brightest part of the sky is directly overhead. It's about 3 times brighter. And that's because you get to the sky much quicker going this way than you do going this way. And this is a real opportunity for us, especially under overcast skies, to think about how and where we want to bring light into our buildings. Another idea is this kind of conceptual approach to daylight design. Now, this is sort of our common approach to thinking about the sun. We we like to put arrows in our drawings, and sometimes we bounce them all around, like we know where they're going. And we usually have a target. Think of that as a work surface where we might have some drawings or a book or a document. And so we talk about a target. And this we might think of as a source path target model. Um, and this is a really good conceptual approach that works well for solar heating and solar control. So if we're trying to figure out how to shade that window, which you all have been thinking about, knowing this profile angle, or sometimes it's an altitude angle, if this window is facing due south and that's noon, we'd want to know that to make a good fixed shading device. Um, but it's not as good for daylight design. So an approach that I'd like to put out there is one that thinks about all of the bright things in the environment that our target sees. And that can be the bright surfaces of the room around us. So that ceiling, this wall, and their apparent size. How much of the visual environment does each of these surfaces um, have relative to this target? And what is its brightness? And we can think of this as the luminance times apparent size. It's really a better conceptual model for daylight design. Um, what we do is we want to consider all the light sources, windows, illuminated surfaces, and their relative size as seen by the target. Now, at the end of Monday's presentation, you saw a whole bunch of really good principles about how to think about windows and those apertures, because these are kind of like light fixtures. They are light fixtures. Um, let's just extend that luminance times apparent size and think of all of the different ways we can create bright surfaces in our buildings. So of course the window is a bright surface, and sometimes it sees the direct sun, but a lot of times it just sees the bright sky. That's what we're really interested in. But we can aim that daylighting to create as many bright surfaces in that space as possible for our targets to see. And this is an idea that our best lighting designers out there knew well. All of our Alto in the Mount Angel Abbey Library in Oregon, in these study carrels, Alto has canted down this surface so that it can see the sky. If it was a horizontal surface, it would just see the ground or maybe a roof below it. But by canting it, this becomes a bright surface that can also be seen down here at this work surface. We see that also playing out in the main area of the library, where these skylights are sculpted in such a way to create a whole bunch of receiving surfaces for brightness that can then be seen by these work surfaces down below. Alto was a master of that. We see it in many of his buildings. This kind of sculpted roof that we see, in this case, this sort of sculpted scooped edge that's seeing the brightness out of that window. Same thing here, this sort of canted roof. And one of the things Alto loved to do was to paint these surfaces red, because in this northern climate, which is gray a lot of the winter part of the year, warming up that surface warms up the light as it reflects into this space. I want to emphasize one more rule of thumb that you saw on Monday, and this idea that if we can put our windows as high up in a space as possible, the penetration of that daylight will extend further back. And we use this H 2.5 rule, 2.5 times H rule. It's a rule of thumb. And as a rule of thumb, it's very general. Sometimes we think of the work plane, as Gail described on Monday, as our H. Sometimes we think of the floor plane. But the idea is to get the glass as high up as possible in the space as possible to extend usable daylight into that space. Now, obviously, the size of that aperture is going to affect the quantity, but it's really the height of that window that guides how deeply into that space the daylight will fall. And this was a really important principle that we applied in the daylight design of the Bullitt Center here in Seattle. And the idea was to get the glass right up to the bottom of the ceiling. This was done structurally by taking the beam that spans from this column to this column and actually turning it up into the floor plate up above so it's hidden, so we can get the glass all the way to the top and extend the daylight portion this full 30 feet. That was another important principle in the design, which is in a living building, under the living building rules, you can't put a occupied workstation more than 30 feet from an operable window. The architects were guided by that 30-foot principle in developing the floor plate. And in the final development of the floor plate of the Bullitt Center, the upper floors were pulled back from the edge, you go back from the edge to create this area around the perimeter that can be occupied by workstations. And then the core can be occupied by bathrooms and by meeting rooms and service spaces. And the result is, as you can see here, in that perimeter zone is a high level of useful daylight and a high level of daylight autonomy, a principle that you heard on Monday, this idea that we can rely on daylighting, in this case, about 92% of the working hours across the entire year on all of those office floors. I think another important principle, shading, and lighting and shading are always in close, sometimes competition with each other, is this idea of operable blinds. Now, I'm a big fan, and I learned all about fixed shading devices in ARC 140. What I learned coming to Seattle was we have a lot of overcast days, and the beauty of a movable shading device is it gets completely out of the way on an overcast day. So you have nothing blocking the bright portion of the sky. The nice thing about these shading devices is they're also outboard of the glass, and these glass windows pop directly out about 8 inches. So the windows can open and close without interfering with the blinds coming and going. One last principle, I'm looking out a window right now that looks just like that. That's the view I'm seeing out my window. Gail showed you this building in Tucson on Rick Joy's office. And this is a wonderful example of the value and the beauty of north-facing windows. So imagine if this window was facing south. What we would be seeing, hopefully this overhang would be shading that glass from direct gain, but we'd be seeing a shaded courtyard. It'd be significantly darker. But by looking out onto a bright, illuminated surface, this space inside is nice and bright. And I experience that every sunny day, which it is today, because this building across the street from my office is nice and yellow and bright, and I'm getting great daylight. Okay, so why is daylighting such an important and powerful tool? I would make an argument this way. First of all, as you saw on Monday, we don't technically see light or lumens, that electromagnetic radiation coming from the sun or coming from an electric light source, this electromagnetic energy that passes through space. What our eyes actually perceive is luminance, the brightness of that energy once it bounces off of surfaces and reaches our eyes. And upon receiving that luminous energy, our eyes convert this photometric energy through nerve impulses, and it's sent to our brain into information that gives our brain all kinds of information about shape and perspective, cues about different distance, and paints these forms with hue, with color, with shade. So architecture truly is a medium to direct, to moderate, and form light. So perhaps it's more accurate to say that light is the form giver of architecture. Now, the connection and relationship of the interior environment with the exterior environment has historically been a source of challenge and order in architecture. Building forms are generated to maximize the penetration of useful daylight. We just saw that in the Bullitt Center. That building was shaped really around the idea of daylighting. And it's the skin of our buildings that are designed as that interactive connector, or filter, or switch, creating not only the necessary connection we have with the outside, but really with furthering that daylighting delight. So one of my arguments for the importance of daylighting in architecture is that this is our real opportunity for us to exercise this traditional relationship between light and form by connecting the interior with the exterior by way of the building's form, and most importantly, through its skin. One of my favorite buildings is this church by Juha Leivaska in Finland. And what Leivaska is doing in this is using the skin of the building as this interactive filter, this selective filter, rather than some kind of indiscriminate barrier. One of our opportunities as daylight designers is to really enlarge our sensory palette. Now, arguably, we don't fully engage all of our opportunities for engaging our senses of sound, our thermal senses, touch, and smell. But light is the king of them all. It overwhelms all of our senses. And because light really gives form to our architecture, it is the principal medium of architecture. It is what makes architecture architecture. You all are going to have the opportunity to do design, both in 140 and in your design studios. And when we think about these very special places like these art galleries, we can see all kinds of really wonderful examples of using these apertures, using both daylight and electric light, light is light, to really create the kind of architectural spaces that make beautiful architecture. We see this at the Therm Valls by Peter Zumthor. Light really charges our senses. Being that dominant sense, it really can overpower all of our other senses. We gain something like 87% of our information through those of us who are sighted, through our sense of vision. And vision doesn't occur, obviously, without the absence of light. So this whole process of perception and sensation of light, starting with electromagnetic radiation, reflecting off of surfaces, it reaches our eyes, lands on the movie screen of our brains, the retina. It's transmitted as nerve impulses back to our brain and translated into images. And we see these lovely images, such as this room in Kentucky, with this single simple aperture and these bright receiving surfaces. And I would argue that this idea of perception is really a process of one thing leads to another. Our brain loves that game. every image that we see triggers a whole family of emotions, of associations, of feelings. Much of this is at the unconscious level. Our conscious thought is really the tip of the iceberg, but it's really what's underneath that helps guide our perceptions. We know all about this from advertisements. Clever marketing can show us an image that immediately triggers a whole family of associations. And in a sense, architecture is no different. And architects have always understood this. And that connection between the interior and the outside has been, as we see in this image, a really, really powerful source of order and orientation. So what I'd like to present then is a way of tapping into these emotions. And this comes from this man, Richard Kelly. Richard Kelly, uh, 1910 to 1977, was really one of the pioneers of architectural lighting design. He taught at Yale and Princeton and Harvard, and he was an influential lighting designer in New York during the middle of the 20th century. He worked with many great luminaries of the age, Mies van der Rohe, Philip Johnson, Eros Saarinen, and Louis Kahn. And he said this, and I quote, "Lighting is such a large part of the visual arts, architecture most of all, that I'm sure the best we can do today will be inadequate tomorrow." And he was speaking in the mid-50s. "I can logically project a great many techniques in lighting to improve people's lives or to make a house more beautiful, but it's all theory until we have the record of experience, which we are only beginning to write." This was in 1958. What Richard Kelly did was he had this idea that um, there are essentially three types of stimuli producing visual perceptions, and that each of these perceptions evokes a set of emotional responses. And he introduced this theory explaining in front of the mind's eye are three elements in the perceptions of visual design, three elemental kinds of light. And they are ambient luminescence, focal glow, and plays of brilliance. So by putting the character and the quality of light into these three categories, but then more importantly, trying to understand the kind of associations we have with these qualities of light, what they tell us, and the responses they trigger, that these can be used by lighting designers, by architects and designers, to choreograph our architectural spaces. So let me see if I can unpack these just a little bit. And let's start with ambient luminescence. Ambient luminescence is the background lighting that serves our need to navigate in the environment. It's that uninterrupted light of a snowy morning in open country. It's the fog at sea in a small boat. It's twilight haze on a wide river where shore and water and sky are indistinguishable. I think of it as that kind of milky white light on an overcast day in a snowfield. It produces a kind of shadowless illumination. It minimizes form and minimizes bulk. We see it at play in Louis Kahn's iconic Kimball Art Museum in this use of ambient luminescence in this ceiling vault illuminated by sunlight and pulsing over the course of the day. Now, I studied this building for years and years and years and have admired it, but only visited it in person for the first time this last summer. And I was really blown away by by experiencing this space. I was there on a mixed sky day in July. Clouds were coming and going, big fluffy white clouds and blue sky. And as you experience this space on a day like that, it breathes, it modulates. The level of light subtly shifts up and down. It really feels like the building is alive. I think it's an example of biophilia, that connection to nature. And we can see in a space like this, in combination with focal glow, a kind of space that's really ideal for um, viewing the treasures inside. Some of the perceptions and associations we have with this kind of light, it does minimize bulk, it can dematerialize space. It can create a suggestion of open space, sort of expanding the space. Walls and ceilings tend to recede. It minimizes the importance of anything individual in that space. It's a kind of egalitarian light. It can be reassuring and it can be restful. It's the kind of light we need to navigate space. And it's the kind of light that we seek when it's done well in workspaces. It's a glare-free light. It's good to have light in a workspace like this coming from the ceiling so that it's not in the same plane as the screens we're viewing on our desk. Windows can create a source of veiling reflections on these screens. So when we have this kind of uniform light, we have the sort of light that allows us to get around and to navigate a space. And that's the goal of these kind of um, light sources, these pendant lights that are providing ambient luminescence so that we can move around these spaces. But we have to be careful because used alone or used poorly, it can be a cloudy day without those heartening rays of sunshine breaking through the clouds. It can be those kind of spiritless classrooms that we've all been in that are dull and flat and kind of lifeless. So in order to really use light well and use ambient luminescence well, we need to add to it another kind of light. And this is my favorite, focal glow. Focal glow is that fire that we tell stories around. Richard Kelly defined it as the follow spot on the modern stage. He said, it's the pool of light at your favorite reading chair. It's the shaft of sunshine that warms the end of the valley. It's the candlelight on the face and a flashlight on a stair. Focal glow draws our attention. It tells us where to go. It tells us what's important. We can see that here again at the Kimball Art Museum. It has this effect of drawing us towards the altar, towards the front of the room. It can be used in these kind of mysterious ways to use color and hue to paint surfaces. It also sells merchandise. It tells us where to direct our attention. It separates what's important from what's not important. It leads us to this information desk or down this hallway or to these displays in these cubbies. Some of my favorite ways focal glow is used effectively is in these kind of ways that we light tables in restaurants or at home. It directs our attention, tells us what's important, and it helps create subspaces within a room. We've all seen this in restaurants where you have a number of tables in a room, but each is in its own pool of light, in its own sort of luminous space. These kind of warm gathering spaces are virtually nothing but focal glow, a room illuminated with focal glow and a few plays of brilliance. So if ambient luminescence helps get us around, and focal glow creates center of importances without any sparkle, interior environments can quickly become dull and spiritless places. So that takes us to the last character of light, and that's plays of brilliance. Richard Kelly describes plays of brilliance as light that can be dynamic, colorful, playful. He says that plays of brilliance is Times Square at night. It's the 18th century ballroom with crystal chandeliers and many candle flames. It's sunlight on a fountain, on a rippling brook. It's a cache of diamonds in an opened cave. It's the rose window of shards. Plays of brilliance excites the optic nerves and in turn stimulates the body and spirit. It quickens the appetite, awakens curiosity, and sharpens the wit. We can see it done really effectively with daylight in these spaces, and it can be done effectively with electric light, as in these places, sort of painting with electric light. I think used effectively with focal glow, these are a couple really good examples in restaurants where you have these sort of stars in the sky, and then concealed up here very, very quietly are these recessed downlights that are illuminating these surfaces in this room. Richard Kelly warns us that used poorly or used alone, that plays of brilliance can be distracting. They can be a source of overstimulation, and they may just be evoking the wrong reaction. And Richard Kelly stressed that visual beauty is perceived by the interplay of all three kinds of light. And so if we want to use this idea to choreograph the illumination in our spaces, we want to know what kind of emotion or what kind of associations we're interested in, and then how to choreograph the light accordingly. So in this space, we see these source of ambient luminescence, and then these recessed luminaires that are providing focal glow. And in fact, when we look out on the built environment, and especially spaces that are well illuminated, they're usually a combination of those three kinds of and three characters of light. So we see again a number of cases of focal glow, these bright surfaces really being a source of ambient luminescence, and then little subtle glints of brilliance. So used well, used effectively, um, like Saarinen's chapel at MIT. We see a really lovely example of those characters of light being brought all together. And then back to the Mirimäki Church in Finland by Juha Leiviskä. Here's another one of my favorite architectural spaces. This is the Rock Church in Helsinki. It has a copper ceiling that sort of glints and sparkles, this source of sometimes ambient luminescence and sometimes shafts of focal glow. And then all in service of illuminating this rich kind of cave-like environment. Okay. I'd like to pause there for just a minute, take a breather, and see if there are any questions, um, or see if you have some thoughts on the question I asked at the beginning of the presentation about why lighting matters and what some of our opportunities are. Does anyone have any questions or comments?
And just to remind people, there's a couple ways you can do this. You can raise your hand, and the GSIs are helping me monitor the participant list so that we can call on you, so we can hear your lovely voice, or you can type in a question in the chat, and we will also be monitoring that to share with Rob. And we know this environment is awkward, but we're stuck with it for a while. So let's see if we can get it a little bit more interactive. Here's a question I see. Somebody is asking if you design by doing daylight simulations. So if you can speak a little bit, Rob, to the methods you use when you're approaching a project. Thank
Yeah,
you, Michelle.
that's a great question. Um, I'm a big fan of daylight models. Um, we did both digital simulation and daylight modeling in the Bullet Center as one example. And we found that both as a design tool, but also as a communication tool, that there's really nothing like a physical model. It can be done quickly, and they make it easy to very quickly explore a number of different opportunities, from color of outside surfaces, color of inside surfaces, size of apertures, direction of light, character of light, to get really quick feedback. To get more quantitative information, the kind of digital simulations that we did later in design to really help quantify and provide evidence. So I think at the design stage, daylight models are terrific. At the evidence stage, there's nothing like a good digital simulation. As more questions come in, we'll have another pause in a minute.
Okay,
I'll
that's
return.
great, Rob. We'll hand it back to you. And then
Okay.
also just a note to people, we're getting used to this medium as well. And our intention is to go back to lectures after the fact. And if there were questions that didn't get answered, we would put those on Piazza on B courses. So please feel free to post questions, whether or not we get to them during the lecture or afterwards. All right, Rob.
I have one question, one
Yeah.
quick question that I could, if I could ask. Do you know
Sure.
when Kelly started working with Lou Kahn? Just out of curiosity, did he work on the Kimball project, and did he work on earlier projects? What was if you know anything about that connection?
Yeah, I'm not certain if he worked on the Kimball or not. He lived until 1970, so I'm not sure how that timeline worked. So I don't know. He's a really interesting man, and I think I was just looking up some information about him in preparation for this lecture, and there is quite a lot written about him. And I think there's still a lot to be learned from him. So thanks for that question.
Rob, we have a couple of questions in chat. The
Sure,
first
Bill.
being that a lot of these projects seem to be in open areas, and how would you design differently in a dense urban environment?
Yeah, that's a great question. I mean, I think what you want to think about is the opportunities that you have in all environments. I mean, I'm sitting in an urban environment right now, surrounded by buildings. And one of the really important things to try to predict is the kind of reflections you see off of other buildings. So again, I'm facing north here, looking out at an 8-story building and then a 4-story building. And they're really warm, light colors. And that makes all the difference. So knowing the surface characteristics and the scale of what's around you in an urban environment. And then, of course, don't forget to take advantage of what's coming in directly above you. when you get to the top of the building, so the sky.
Great, thanks. And a second question that we had was looking back at your project in Seattle
Yeah.
with the high glass windows. How did you deal with glare? Was there a setback process that you dealt with the glare?
Yeah, no, that's also a good question. There's two ways that the glare was addressed in the Bullitt Center. One is with the movable shades. The way they work is they are on an astronomical clock. So they know the altitude and the azimuth of the sun for every time of year. There's also a weather station on the roof that says, is it sunny or is it not? So if it's not sunny, the blinds stay up, and glare from a uniformly overcast sky is addressed on the inside with roller blinds inside windows. On a sunny day, the primary glare control is also the shading device. The blinds deploy on the side of the building where there's sun, and they continually adjust to keep direct beam radiation from hitting the glass. So it's a two-part thing. Glare control on the inside, shading device on the outside, and they're working in partnership with each other. The shades on the outside are automated, and users don't have control over those, but of course the blinds on the inside are user controlled.
Great, thank you.
All right,
Okay, Rob, ready to return to your lecture. Thank you for that. That was helpful.
sure. So I want to switch gears a little bit, and I'm going to switch into the idea of electric lighting. Now, when I studied lighting um, 100 years ago at Berkeley, Professor Peters, Dick Peters, wanted us to really understand that light is light. It's electromagnetic radiation, whether it comes from the sun or whether it comes from an electric source, it's all light. And if we know what we need to do as designers is learn how to direct that light. And the way we do that is with light fixtures. Windows are a type of light fixtures, and luminaires. Luminaires is what lighting designers call light fixtures, and they're a way to direct and distribute light. And so an additional metric that we need to know, which you were introduced to on Monday, is this idea of luminous intensity measured as a candela or a CD. And this is the directional quantity of light. It's the energy from one candle, a unit of light, flowing through one solid angle called a steradian. There's 4 pi steradians in a sphere. And I think this is a pretty good analog. Think of it as a sprinkler, a fire sprinkler, and a kind of cone, and how much light comes through that cone. Now, it's not distance dependent, because however much energy comes through that cone is the same no matter how far away you get from that source. But of course, it gets spread out over a larger and larger area, so that that energy gets diluted over more space. And anytime you buy a luminaire, a light fixture, it should come with a candle power distribution curve, which shows you how that light is distributed. And so these radial lines tell you how many candelas, and these radial lines tell you in what direction. So this is a very common shape for a recessed can light. There's no light going up into the ceiling. It's all being directed down, and it's being directed down into this particular cone of about 30 degrees in each direction. And there's this bump, this characteristic bump. This is sometimes called a bat wing, so that you have a little bit less candle power coming straight down than off to the side, because this energy has to travel further before it hits a surface. So the result is a fairly uniform pool of light underneath that recessed can. So every light fixture you buy will have something that looks like that candle power distribution curve. And here are some more generic ones. The lights will also be characterized as being an indirect. In other words, this is some kind of suspended light fixture, and all of its luminous energy is being directed up to the ceiling. Semi-indirect, the majority going up, a smaller proportion going down, or direct indirect, where approximately the same amount of energy is going up or down. Diffuse, energy is being distributed uniformly. Semi-direct, the majority being directed downward, and then a direct, and here are two different directs, one more of a spot and one more of a broad diffusing direct light. So these would be examples of recessed cans. Here's another couple shapes of candle power distribution curves. Again, that characteristic bat wing idea. This also helps reduce the amount of light coming directly down to reduce the potential of glare or veiling reflections off of a surface. This is going to produce a more uniform pool of light with a little bit of light going directed up towards the ceiling for a little bit of ambient luminescence. So now some terminology. This is going to help you specify or select light sources or luminaires. There's this idea of valences and cornices. A valence is this sort of luminaire with a shield over the light source, typically a fluorescent tube against a wall. Light can go up and brighten these surfaces or wash the wall below it. Or a cornice. Skiers know this one. Here's a cornice, shielding the light source and washing this surface. So we can see this idea of light as a way to brighten surfaces. We want to create bright, luminous surfaces in our environment. Here's some nice little rules of thumb for cove, and these slides will all be available afterwards. And a cove light, which is pretty common, is a way of concealing the light source to illuminate an upper wall and a ceiling. And this little illustration here describes some of the kind of rules of thumb for the geometry of a cove lighting system that you can come back to. So here's an example of cove lighting. So coves are generally used to direct light towards a ceiling, providing a kind of ambient luminescence. And we see here a good example of ambient luminescence. And then you can see concealed up here that source of focal glow, illuminating the tabletop, and then some plays of brilliance. So all three characters of light are at play here. Here's another cove. And here, these are being produced with cove lighting that's above this kind of floating surface, and cans, recessed cans to provide that focal glow. Bright ceilings surfaces will tend to recede as we illuminate them. Here we see coves and cans, recessed can right there, and in this sort of wine cellar. And then kind of here on the altar of vino, one special source of focal glow. A chandelier is a classic source of both ambient luminescence and some bling, some plays of brilliance, and then we can see these cans in here that are providing focal glow onto these surfaces, onto these tables. And another example of coves. When you're out there specifying light fixtures, you've probably heard of these, pendants. Pendants are a kind of light fixture that hangs down like a pendant necklace from the ceiling. These happen to be a Bega light out of Germany. Nice pendant. Sconces. Sconces refer to this whole family of light fixtures or luminaires that rest against a wall. and provide a source of wall washing. You're all familiar with various kinds of tracks. These are now a little bit anachronistic. These MR16s, these halogen incandescents, which are now being quickly replaced by LEDs, but the same idea, tracks, and this way you can direct light where you want it. Surface mounted are distinct from pendants because they go right up against a ceiling and tend to distribute their light mostly down. These are from a company called in the Bay Area. This is their starter home collection, and this is another Bega lamp. There's luminaires that are a particular kind of sconce that are uplights. Another family of bollards. These are useful for keeping traffic separated from sidewalks and walkways from roadways. And this is a whole family of, again, Bega bollards, a really nice set of modern bollards. Torchieres, generally my least favorite light fixture, but in a space that may not have any source of ambient luminescence built in, these can be a good substitute. Table and desk lamps, the kind we're most familiar with. These, by the way, are a Louis Polson family of lights. So that's how we direct light. The other thing we want to know is something about light and color. And light and color is a function of the light source. And if the sun is our light source, we see this full spectrum, the full electromagnetic spectrum of light. The receiving surface, and in this case, if it's a red surface, what's happened is that red surface is absorbing most of the spectral content of that, or a lot of the spectral content of that sunlight, and reflecting just the red portion of it. And that's why it looks red. And then the third part is our perception, our adaptation state, our expectation, and the health of our visual system. Now remember that when we're talking about the visible spectrum of light, we're talking about a pretty narrow part of the electromagnetic spectrum coming from the sun. It's this portion that's between about 380 nanometers to about 760 nanometers there. Played out on a graph, if this graph as a function of wavelength down here and intensity here, the part that our eyes can see is this visible, what we call the visible portion. Now, of course, because we've evolved in sunlight on this planet, our eyes turn out to be most sensitive to the most intense part of the solar spectrum. But it's really just this part of the spectrum, nominally from about 400 to 700 nanometers. And when we get to shorter wavelengths, we get into the blues or the ultraviolet. And when we get to these longer wavelengths, as we move all the way out here to heat, room temperatures, we get into the near infrared. So this is the red, orange part of the spectrum. This is the blue violet portion of the spectrum. And when we look at light sources, the light bulb itself, while the luminaire directs the light source itself has a characteristic spectral power distribution curve. And it's a graph of relative energy emitted at wavelengths by a light source. This is characteristic of an incandescent light. It produces a majority of its illumination in the warmer part of the spectrum. Here's a fluorescent lamp, which has these odd spikes because the light that it's producing is being produced by interaction of a electric arc traveling down that tube, interacting with the phosphors that are coating that tube. And depending on what phosphors there are, you'll get a different shape here, and then these spikes of light. And then when we get into these high intensity discharge lamp, this is an old fashioned mercury light, which I hope we never see again. It has very odd light, and this is why the light from it looks very strange. So if we look at those together, again, here is our incandescent light. Its spectral content a lot more warm, longer wavelength. Here's daylight. This is the kind of light that we would see from the blue portion of the sky. And it's much more even, but it has a lot more blue light. So it tends to be a bluer, whiter light. And then here's that strange fluorescent light. So if we look at those together, depending on the light source we use, we're going to have a very different spectral distribution of light. We might think that a daylight lamp would be best because it looks full spectrum. But the fact is that full spectrum at the levels of light produced by an electric light tend to look very cold and white, and they don't render humans very well. This is a much more common and easy on the eye light source, and it renders skin tones really well. This is a really strange light, a low pressure sodium. We don't see many of these anymore. Any of you who are from San Diego, there used to be a lot of low pressure sodium lights. That was to keep light at night in a very narrow spectrum so that the astronomical telescope on the hill above San Diego could filter this out and essentially have dark skies. But it rendered everything kind of yellow brown. And if you were in a parking lot and you had a kind of, Toyota Corolla like everyone else, you might get into the wrong car. I want to emphasize that when you look at these spectral power distribution curves, what really matters is the proportion of light. So what we see down here is a 3000 K light, which is the colored portion, a 2800 K light, lower color temperature, but a higher proportion of red. And then the higher temperature light, which is this curve up here, has a slightly higher proportion of blue relative to red and tends to be a little bit whiter. And this is another illustration of that. So when you buy a light, every light that you buy at the hardware store will have a color temperature. And the lower the color temperature, the warmer the light. I recommend for a house that you don't use anything higher than 3000 K or 3000 Kelvin. There's another metric for measuring the color of light. It's this color rendering index, CRI, and it's a subjective measure of light. It's a way of measuring light visually, looking at two lights, at a reference light source and the light source being tested, and then these color samples and a subjective observer. What you need to know if you come across the CRI is it's a single number measure. The closer to 100 means a closer or an exact color match with the surface you're trying to color. And this sort of illustrates that. So if these are three color swatches, this sort of represents 4 different light sources and the way they might render the color of those surfaces. In this illustration, it says fluorescent is the best because the blue gets a little washed out. I might take exception to that. Incandescents generally render colors better than fluorescents. I want to finish with one last element to help you with your lighting design now and in the future. And this is how to choose the source of electric light. And the measures that we're going to use are efficiency, color, life, and cost. And when I first studied light in undergraduate school, we had to learn a whole family of discharge lamps and our more familiar incandescent lights and how to identify what they were based on a set of numbers. And in the discharge lamps lights, there's the standard intensity, and then there's the high intensity discharge lamps. And in the incandescent family, there's tungsten, halogen, all here in standard voltage, and then low voltage. So you can see there's a lot of flavors of light. And we're not even going to worry about this because these have come along, LED, light emitting diodes. And in your futures, I think it's probably still as an informed designer that you know about these lights on the way out. But the truth is, these are the light sources that you're going to be using in the future. And here's why. If we look at light sources and our selection criteria, we're interested in their color, either their spectral power distribution, their correlated color temperature, or their color rendering index. So their correlated color temperature, again, you'll see on the boxes of every lamp a color temperature. And as you get down here from 3,000 down, these tend to be the warm lights. Above 3,000, especially above 4,000, you get into white and very blue lights. Their efficacy, we want a light source that produces as much light per watt as possible. And then we want them to last a long time. And in our old-fashioned light sources, they sort of got dimmer and dimmer, just like me, as they get older until they have an end of life. And so we're interested in where are they at still 80% of their brightness? How long does that take? So let's do a quick comparison between these three light sources. They have different power, but they all produce about the same luminous flux. So roughly 800, 850 lumens. So these are all equivalent in the amount of luminous energy that they produce, but they have very different amount of input energy. And that's measured as efficacy, or lumens per watt. And we want a light source with as many lumens per watt as possible. We also want them to last a long time. And here we can see LEDs are really winning the race. And this is the great part. 10 years ago, this was a $15 lamp, and now it's a $3 lamp, more or less. So these are approximate costs of these. And if we look at their lifetime costs, and lifetime, I'm going to say is 25,000 hours, we're going to have to buy a whole bunch of 25 incandescent lights and replace them over 25,000 hours. And it's going to cost us $365 and change. The fluorescent light is going to cost us $58.30. And it comes with some toxic baggage, some mercury that's in that lamp, versus the LED. Our final criteria really is color. And incandescents, as I've said before, have excellent color. Fluorescents are okay. And LEDs are pretty good and getting better all the time. And the other great thing, as many of you know, is you can tune these. You can change their color, and that's pretty cool. So finally, can they be dimmed? The answer is yes, possible, and possible. One thing you have to know is you have to have the appropriate dimmer switch in order to dim an LED lamp. And you have to buy one that is dimmable. So pay attention to that when you're buying your LEDs. Here's what they look like. Manufactured light sources, a whole family of them. And just for your information, A, which is our standard one, stands for arbitrary, G, globe, T, tubular, F, flame. You can see all that. And then these numbers down here, a 15 or 19, that stands for the diameter at its widest point. So our common A19 lamp is 19/8 of an inch. It stands for an eighth of an inch. An MR16 one of my favorites, a metallized reflector, 16/8 of an inch in diameter. So a little arcane knowledge for you. Here are our discharge lamps. They come in low intensity and high intensity. They all require a ballast to control the current because they operate by sending an arc from one end to the other time, exciting phosphors or gases inside, either in a little capsule or in the enclosure itself. But they all require a ballast, which in these ones is concealed in this base, this little heavy base, that's a ballast. And for these lamps, it's concealed in the luminaire. So these all require a special luminaire, and they're really fussy. And these are the lights we're going to be using now and into the future. The great thing about them is not only are they efficient, not only do they produce really pretty good color, but they're pretty small. So we can use a really tiny source and then use our luminaire to direct that light wherever we want. And the result is, here's an incandescent scene. There's our old-fashioned lighting there. Here's our HID, typical in big box stores and gymnasiums, arenas. These would have been metal halide lamps. Sports stadiums, parking lots. And these are all being changed out very quickly to LEDs. So there is an LED parking lot with high pressure sodium, also a very sort of yellow pink light. And then the new LEDs, more efficient, generally better color. They're being used to replace high bay lighting in warehouses and big box stores. And they're being used in all kinds of applications, some kind of playful to create color. But with LEDs, we can achieve Richard Kelly's 3 kinds of lighting. And we can play with color. But we can achieve the same kind of lighting scenes that we could with our incandescents, and we can do it with a lot less energy and a lot more control. So these are our future. There's a lot of great possibilities with them. We can play with these lights, create space with these lights, and create really well illuminated environments using daylight and electric lighting to create these kind of marvelous spaces that we want to visit and we want to stay in. So you all, thanks for spending the last hour and some with me. If there are any questions, I'd be really happy to field any questions. Thanks a lot.
Thank you, Rob. That was fabulous. So much inspiration for people's design projects. So again, we've got 2 different ways that you can try to engage. You can raise your hand and the GSIs will try to monitor that, or you can type in a question and we will monitor that as well. I'll start it off. I think there was an earlier question that may not have gotten asked, and this is about the project in Seattle with the really high glass windows.
Yeah.
And how you dealt with glare, or was the setback process the way in which you did that?
Yeah. And I didn't answer that question fully. And this was really in the realm of my colleague, who really is a well-known daylight designer, Chris Meek. And Chris Meek worked with the tenants because the Bullitt Center is a shell and core office building. So while the shading devices are part of the shell and core, they're part of the building, all of the interior design is part of the tenant's responsibility. So every tenant had different needs depending on what their work is, and different aesthetic preferences. And so Chris Meek and other daylight designers worked with them for their specific needs. And there's, of course, a whole family of window control, shading control, glare control strategies that you can use, from mesh screen to louvered blinds. And all of those were used in different ways around the Bullitt Center. We also have to remember that in Seattle, about 8 months of the year, we have many of our days are uniformly overcast. And what we found there is really because that 30-foot area around the perimeter of the building is so uniformly illuminated with large windows, most of the tenants don't need any kind of glare control most of the time.
Well, that's a good point. So you're not getting the direct beam, which
Right.
is what shoots up illumination levels pretty high. And because you're not getting these patchy windows and then dark walls combined with the overcast skies, that it is a little bit more uniform. So you're not getting the contrast.
Right, right. And Gail, you bring up a good point. One of the modeling exercises that was done was how to distribute the windows. Now, sort of the classic daylight mode is to provide a uniform strip of horizontal windows up high against the ceiling, primarily for daylighting, and then bringing in more controlled bits of glass window for view and for daylight where people are. Because of the construction of the Bullitt Center, it was more cost effective to bring the windows in big vertical panels of curtain wall that extend from floor to floor to floor with spander glass, in other words, insulated areas behind portions of the window that aren't needed for lighter view. That was a better way to get have fewer places to seal and lose heat and air along the windows. We were concerned that those sorts of rows of windows with rows of opaque wall might create a kind of illumination that wasn't very uniform. And it turned out that because of the proportion of window to wall and the light colored surfaces and bringing windows to the ceiling, that the daylight distribution was really almost as good as any of those other ways of bringing light in horizontally. But we didn't know that until it was really modeled.
Right, interesting. So another question that came in, moving to electric lighting, is that we hear a lot of we hear a lot about the pros of LED lights. Are there any disadvantages, either environmentally or from the designer's point of view, from the human response point of view?
Yeah. I'm going to give you a pretty narrow slice because I'm not really an expert in LEDs, and I don't know if they have in their manufacturing or in their return to the cycle any negative consequences. They don't have the little bits of mercury that fluorescent lights have, so that's a good thing, but I don't know what other materials they might have. In my experience, the light generally does not have the same kind of uniform spectral distribution that incandescent lights have. And so my perception is the light is a little different, and sometimes just a little bit odd, because portions of the spectrum aren't what I'm used to from an incandescent light. And this also goes back to our biological past. We evolved in a situation where, as the light levels from our environment reduce, either from daylight to fires, the light becomes warmer and redder. So we're programmed to have a preference when we have low lighting for it to be very warm, and when we have very bright lighting for it to be very white. And so trying to match that indoors where typically we have, relative to outdoor light, a fairly low level of light. And that's why I'm a big fan of generally having warmer color temperatures indoors, because that's what our eyes and our brains are tuned to at the level of light that indoor lighting provides.
And in my understanding with the LED lights, and I think you had mentioned this, that you can get one bulb that's tunable. So you can start changing the morning and evening patterns to better match the natural rhythms and impact our circadian health in positive ways. And I think that's a really interesting innovation that we haven't seen with any other light sources. And I'm seeing it more in experimental facilities and in research. It hasn't been widespread yet, but I think that could be a direction that things are going.
It's really exciting.
Oh, that's great.
Yeah.
Any other questions from the crowd in the last minute or two we have here? I'm scrolling through the chat, not seeing anything that I don't think we've covered. Well, Rob, I just want to end then by thanking you from the bottom of my heart. That was really inspiring. I'm sure the students are going to go back to the slideshow and look at the images and maybe get some ideas for their own design projects. And I know things are pretty crazy where you are as well with the remote teaching and the restrictions. So we wish you well.
Well, thank you, Gail. And I'd like to put out a shameless pitch to those undergraduates who, when you're considering a graduate program, some of our very best recent graduate students in our MARC program are from your school. So feel free to contact me if you're interested in considering the University of Washington in the future.
Well, I would add to that, you have a fabulous program. It's a great school. It's a great location. My daughter goes to University of Washington, not in architecture, but I can speak from that point of view to just what a wonderful location and education she's getting. We couldn't be happier. So,
And my son is a freshman at Cal, so
yeah.
the Bears.
Rob and I are trading kids right now in terms of where they're each going. And Rob's been a great soul and looking out for my girl, making sure she does okay. So with that, we're going to close the meeting. I see a lot of chats coming in that just say, thank you, thank you, thank you. Amazing lecture. So a lot of voices of appreciation that just keep rolling in that make me so happy and warm my heart. Thank you, everybody, the students, for your attitude of gratitude. And again, stay tuned. The GSIs and I are figuring out what to do with the design project, and we will be communicating with you virtually this week. Bye, Rob. Thanks to all.
Bye-bye. Thank you all for your nice chats.